In this video, we shall see how we can use an infinite series to solve some difficult differential equations. Before we get into that, a little bit of notation. When I write y with a straight line a, or dy by dx, a, or d2y by dx squared, a, what I mean is the value of y, or dy by dx, or d2y by dx squared when x equals a. We should be familiar with the Taylor series. F of x plus a is f of a plus x f dashed a, etc. And using the above notation, I can write this as y, that's your function, is y when x equals a, plus x times dy by dx when x is a, plus x squared over 2 factorial times d2y by dx squared when x equals a, and so on. In particular, if we put a equal to 0, we get the Maclaurin series, and we can use y is y when x is 0, plus x dy by dx when x is 0, and so on. Your tables give you, your formula booklets give you this formula. They do not write it in this form. It's not difficult to get from one to the other, and you should have no difficulty in doing that. Use a Maclaurin series to solve the differential equation y d2y by dx squared plus dy by dx all squared plus y is naught, which would be rather difficult to do with any of the techniques. We couldn't use any of the techniques that we've had so far, up to the term in x cubed, given that y is 1, dy by dx is 2 when x is naught. I've added the Maclaurin series for you, and here is the condition that y is 1, dy by dx is 2 when x is 0. So we know y, we know dy by dx when x is 0. This enables to work out d2y by dx squared when x is 0. So if we put that information into A, y is 1, d2y by dx squared when x is 0, plus dy by dx, that's 2 squared, plus y is 1, and that gives us that d2y by dx squared when x is 0 is minus 5. So we're on the way. We can get as far as here. We now want d3y by dx cubed. All we have to do is to differentiate this equation. If I differentiate this equation, I will get an expression with d3y by dx cubed. So d by dx of a, first one is a product, y, differentiate d2y by dx squared gives me d3y by dx cubed, plus differentiate y gives me dy by dx, d2y by dx squared, plus if I differentiate dy by dx all squared, that is chain rule. That's 2 dy by dx and differentiate dy by dx. Plus differentiating y, I get dy by dx, and equals 0. Now let's put x equal to 0. X equal to 0, y is 1, so that gives me 1 times d3y by dx cubed when x is 0, plus dy by dx, which is 2, times d2y by dx squared, which is minus 5, plus 2 times dy by dx, which is 2, times d2y by dx squared, which is minus 5, plus dy by dx, which is 2, equals 0. And that tells us that d3y by dx cubed, when x is 0, I've got minus 10 minus 20 plus 2 is minus 28 is 28. So all we have to do now is to put the different values in this expression here. Move up a little bit just to give myself a bit more room. Therefore, y is y when x is 0, which is 1, plus x times dy by dx, that's 2, plus x squared over 2 factorial, d2y by dx squared is minus 5, plus x cubed over 3 factorial, d3y by dx cubed when x is 0 is 28. And that we can just simplify to give us 1 plus 2x minus 5x squared over 2 plus 14x cubed over 3. This then gives us a good approximation for y when x is small. We can also use this technique to find an expansion of f of x, or a series for f of x, in powers of x minus a. Here's the Taylor series that, again, you should be used to this one. And we can rewrite this as y equals y when x is a, plus x minus a times dy by dx when x is a, plus x minus a all squared over 2 factorial times d2y by dx squared when x is a, and so on. In this example, we're asked to use a Taylor series to solve x dy by dx minus y squared equals e to the x minus 2. This again is an equation which the techniques you've covered so far would not help. Solve this in ascending powers of x minus 2 up to the term in x minus 2 cubed, given that y is 3 when x is 2. So we want to go up to x minus 2 cubed, x minus a squared. We're putting a equal to 2. So putting a equal to 2 gives us that y is the value of y when x is 2, plus x minus 2 times dy by dx when x is 2, x minus 2 squared over 2 shriek, d2y by dx squared when x is 2, and so on. There is my differential equation. And now we carry on in a very similar way to the previous one. We need the derivatives when x is 2. Let's move this up. We have that, I've just lost it above the top, y is 3 when x is 2. That tells me that 2 dy by dx at x equals 2 minus 3 squared is equal to 2 minus 2 is 0, e to the 0 is 1. And this gives us that dy by dx when x equals 2 is equal to 3 squared is 9, plus 1 makes 10, divided by 2 is 5. As before, we need to differentiate now to get to the next derivative. So if we differentiate b, we will get, first one's a product, x dy by dx, differentiate the dy by dx, gives me d2y by dx squared, plus dy by dx, differentiate x, minus differentiating y squared, 2y dy by dx, differentiate e to the x minus 2 is e to the x minus 2. Now we have that x is 2, y is 3, and dy by dx is 5. That will give me that 2 d2y by dx squared plus dy by dx is plus 5 minus 2 times y, which is 3, times dy by dx, which is 5, equals e to the 2 minus 2 is 1. And if we work that out, d2y by dx squared at x equals 2 is 5 minus 30 is minus 25. Add to 1 is 26. Divide by 2 is 13. We need d3y by dx cubed. So let's differentiate again. That will give me differentiating x d2y by dx squared is a product again. That's x d3y by dx cubed plus d2y by dx squared, differentiate x, plus differentiate dy by dx, minus 2. Now I have to differentiate a product again, y dy by dx. Differentiating y, I get dy by dx times dy by dx plus y, differentiate dy by dx is d2y by dx squared equals e to the 2 minus 2 is e to the 0 is 1. We've got all the different values to put in. X is 2, d3y by dx cubed at 2, plus, I've now got 2 lots of dy by dx squared. dy by dx, or d2y by dx squared is 13, minus 2, dy by dx is 5, so that's 2 times 5 squared, plus y is 3, d2y by dx squared is 13, equals 1, and with a little bit of arithmetic, we should be able to discover that d3y by dx cubed, when x is 2, is equal to 103 over 2. Now we're in a position to use the line at the top of the screen. This tells me that y is equal to y when x is 2, which is 3, plus dy by dx, which is 5, times x minus 2, plus d2y by dx squared is 13 over 2 factorial, x minus 2 squared, plus d3y by dx cubed at x equals 2 is 103 over 2. 3 factorial is 6. 103 over 2 times 3 factorial, x minus 2 cubed. So we now have a series approximation for y near x equals 2. In other words, for small values of x, this will give a good approximation for y at values of x close to 2.